Hello there, and welcome back to Bedtime Science. I am really glad you are here tonight. Somewhere outside, air is moving. It may be sliding quietly along a wall, lifting from a dark roof, descending a hillside, or crossing water that is warmer than the night above it. The motion may be too gentle to move a curtain. It may be part of a wind system spanning an ocean. The air does not know which scale it belongs to. A small difference in temperature changes density. A small difference in pressure begins a flow. Water evaporates from a surface. A rising current cools. Invisible vapor reaches saturation and becomes droplets. The droplets join a cloud. The cloud may fade without rain, travel hundreds of kilometers, or grow until electricity moves through it as lightning. Weather is the history of those changes. It is familiar enough to be checked in a few seconds on a phone and complex enough that no forecast can follow every detail indefinitely. The atmosphere is a fluid wrapped around a rotating planet, heated unevenly by a star, interrupted by mountains, oceans, forests, cities, and ice. Its gases are almost transparent. Its motion becomes visible only when it carries dust, bends trees, shapes waves, or gathers water into clouds. Tonight, we will follow one portion of that fluid. We will begin with sunlight reaching Earth. The energy will warm a surface, alter pressure, and begin a wind. The wind will cross an ocean and carry water vapor. It will rise, cool, and form a cloud. The cloud will enter a larger weather system and eventually produce rain. Along the way, the story will widen. We will see why winds curve instead of moving directly from high pressure to low. We will enter the jet stream, a thunderstorm, a tornado, and the eye of a tropical cyclone. We will meet the people who learned to name clouds, measure pressure, connect distant observations by telegraph, calculate forecasts by hand, and discover that tiny uncertainties can grow. Then the story will return to the air outside. The weather there is one temporary arrangement inside a system that never stops rearranging itself. The atmosphere is often described as a layer. The word makes it sound like a shell with a clear upper surface. There is no sharp edge. Air becomes thinner with height. Molecules grow farther apart. The dense lower atmosphere gives way gradually to regions where a particle may travel a long distance before colliding with another. The Kármán line, 100 kilometers above sea level, is a useful conventional boundary for spaceflight. It is not the place where the atmosphere ends. Traces of Earth's outer atmosphere extend far beyond it. The gases are dominated by nitrogen, about 78% of dry air, and oxygen, about 21%. Argon contributes just under 1%. Carbon dioxide occupies only a little more than 400 parts per million, yet strongly influences infrared radiation. Water vapor varies far more, from almost none in very cold dry air to several percent in warm, humid tropical air. Small fractions can have large effects. Water vapor supplies clouds and latent heat. Carbon dioxide alters the energy balance. Ozone high in the stratosphere absorbs ultraviolet radiation. Aerosols influence visibility, radiation, and cloud droplets. Almost all weather occurs much lower, in the troposphere. The troposphere reaches roughly 8 kilometers above the poles and can rise beyond 16 kilometers in the tropics. Its depth changes with latitude, season, and weather. It contains most atmospheric mass and nearly all atmospheric water vapor. Above it lies the stratosphere, where ozone absorbs ultraviolet radiation and temperature generally increases with height. Above the stratosphere are the colder mesosphere, the extremely thin thermosphere, and the outer exosphere. A thunderstorm that reaches the top of the troposphere is tall by human standards and still occupies only the lower portion of Earth's gaseous envelope. The atmosphere is thin compared with the planet. Yet, thickness alone does not describe its importance. At sea level, a vertical column of air presses downward because gravity holds the molecules near Earth. The weight of that column produces atmospheric pressure. The pressure is not felt as a crushing force because fluids and tissues inside the body push outward, and pressure acts from many directions. A change of pressure is easier to notice. A sealed packet of air expands as an aircraft climbs. Ears respond when pressure outside changes faster than the middle ear can equalize. A bag closed at high altitude swells when carried downward or upward depending on where it was sealed. The measurement of air pressure began with a puzzle about water. In 17th century Italy, pump makers found that suction pumps could not lift water more than about 10 meters. The traditional explanation invoked nature's supposed horror of a vacuum. Galileo discussed the problem but did not fully resolve it. Evangelista Torricelli, one of Galileo's students, tried a different liquid. Mercury is much denser than water. If the atmosphere supports a column by pressing on the reservoir below, a much shorter column of mercury should balance the same pressure. In 1643, Torricelli filled a long glass tube with mercury, inverted it into a dish, and watched the column fall until it stood roughly 76 centimeters high. Above the mercury remained an apparently empty space. The atmosphere was holding the column up. Torricelli had made a barometer. He also wrote that humanity lived at the bottom of an ocean of air. The metaphor remains exact. Fish are surrounded by water and feel its pressure. Humans move beneath a sea of gas. When the mass of air above a place changes, the barometer changes. A falling barometer can indicate that a lower pressure system is approaching, though pressure alone does not determine the weather. A rising barometer can accompany clearing conditions, but high pressure can also trap fog, pollution, or cold air near the surface. The instrument measures one part of a moving structure. Blaise Pascal tested Torricelli's interpretation by asking whether pressure should decrease with height. In 1648, Pascal's brother-in-law Florent Périer carried a barometer up the Puy de Dôme in France. The mercury column fell as the group climbed. There was less air above the higher point. The atmosphere had weight, and its pressure changed through depth. A mountain had become a laboratory. Pressure depends on more than altitude. Warm air expands and becomes less dense if pressure can adjust. Cold air contracts and becomes denser. Air also converges into regions and diverges away from them. Large-scale rising motion removes mass from a column near the surface, while sinking can add it. These processes create pressure patterns. Air begins moving because forces do not balance. The pressure gradient force pushes from higher pressure toward lower pressure. If Earth did not rotate and the surface created no friction, wind would accelerate more directly across pressure contours. Earth does rotate. That changes the path. The Coriolis effect is not a mysterious force produced by storms. It is the apparent deflection seen when motion is described on a rotating planet. In the northern hemisphere, large-scale moving air is deflected toward the right of its direction of travel. In the southern hemisphere, it is deflected toward the left. The effect is zero at the equator and increases toward the poles. It matters most for motion lasting long enough and traveling far enough for rotation to alter the path. A sink or bathtub is too small for the hemisphere to determine the direction of an ordinary drain. Shape, initial motion, plumbing, and local disturbances dominate. A continent-sized air current is different. As wind accelerates from high toward low pressure, Coriolis deflection turns it. Above the frictional influence of the surface, the two can approach balance, producing geostrophic wind that flows roughly parallel to lines of constant pressure. This is why weather map winds do not normally point straight into a low. Near the ground, friction slows the air. The Coriolis effect weakens with the reduced speed, so wind crosses the pressure contours at an angle toward lower pressure. Air spirals inward around surface low-pressure systems and outward around highs. In the northern hemisphere, The inward flow around lows is counterclockwise and the outward flow around highs clockwise. The directions reverse in the southern hemisphere. The rotation is not the cause of low pressure. It is the shape produced as pressure-driven motion moves across a rotating Earth. The wind outside tonight may be local and still carry this planetary history. Buildings and trees break it into eddies. Terrain redirects it. Friction slows the lowest layer. Above those disturbances, the wider flow is shaped by pressure fields extending far beyond the horizon. The first portion of air in our story has begun to move. Sunlight created part of the temperature difference. Pressure translated the difference into force. Earth's rotation turned the path. Now the wind can begin carrying heat. The sun does not heat Earth evenly. Near the equator, sunlight strikes the surface more directly. Near the poles, the same energy spreads across a larger area and passes through more atmosphere. Day and night alternate. Seasons shift the angle and duration of sunlight. Land warms and cools quickly. Water changes temperature more slowly and stores enormous amounts of heat. The atmosphere and ocean respond by transporting energy. They do not erase the difference between equator and pole. They continually work against it. This creates global circulation. A simple non-rotating planet might develop one overturning cell in each hemisphere. Warm air rising near the equator, flowing poleward aloft, sinking near the poles, and returning near the surface. Earth's rotation breaks that simple pattern. In the tropics, intense heating and abundant moisture support rising motion near a shifting zone called the intertropical convergence zone. The name describes where trade winds from the two hemispheres converge. The zone is not a perfectly continuous line fixed on the geographic equator. It moves seasonally and responds to land, ocean, monsoon circulations, sea surface temperature, and waves in the atmosphere. Where air rises, pressure falls with height differently than in surrounding regions. Water vapor cools and condenses. Clouds and heavy rain become common. The condensation releases latent heat. This heat was absorbed earlier when liquid water evaporated. It did not raise the water's temperature then. It became stored in the phase change. When vapor becomes liquid or ice, the energy returns to the surrounding air. Latent heat is one of weather's main ways of moving energy. A cloud is therefore not merely water appearing. It is an engine in which phase change alters buoyancy and circulation. After rising in the tropics, air spreads poleward high in the troposphere. It cools, loses moisture, and eventually descends in the subtropics, broadly around 20 to 35 degrees latitude. Descending air is compressed by increasing pressure and warms. Relative humidity falls because warmer air can maintain a higher saturation vapor pressure. Cloud formation is suppressed. This helps create the subtropical dry belts that include many of the world's great deserts. The Sahara, Arabian Peninsula, parts of Australia, the Atacama region, and other dry landscapes are influenced by descending branches of global circulation, though mountains, ocean currents, continental position, and regional weather also matter. Near the surface, part of the subtropical air returns toward the equator. Coriolis deflection turns it westward, producing the northeast trade winds north of the equator and southeast trades south of it. The trades were known to sailors long before their planetary explanation. They carried ships across oceans with enough regularity to shape trade routes, colonization, migration, and war. The circulation is called the Hadley cell after George Hadley, an 18th century English lawyer and amateur scientist. Hadley tried to explain why the trade winds blow from the east rather than directly from north and south. His 1735 account used the changing eastward speed of Earth's surface with latitude. Air moving toward the equator retains a different eastward motion and appears to drift westward relative to the faster moving ground. The modern explanation uses conservation of angular momentum and Coriolis dynamics. but Hadley's insight connected planetary rotation with wind. His name became attached to a circulation cell larger and more complex than he could observe. Poleward of the Hadley cells lie the mid-latitude westerlies. Here, the atmosphere transports heat largely through moving high and low-pressure systems rather than one smooth, overturning loop. Warm air pushes poleward in some regions. Cold air pushes equatorward in others. The boundaries tilt, wave, and form cyclones. Farther poleward, polar circulations complete the broad three-cell picture often shown in textbooks. The real atmosphere is less symmetrical. Continents interrupt ocean. Mountains generate standing waves. Seasons shift temperature gradients. Storms exchange momentum. The stratosphere interacts with the troposphere. Tropical convection moves in pulses rather than a permanent ring. The three-cell model is a guide, not a photograph. One consequence of the equator to pole temperature difference appears high above the surface. A horizontal temperature gradient creates a change of wind with height through a relationship called thermal wind balance. Where the gradient is strong, upper-level westerlies intensify. Narrow bands of especially fast wind become jet streams. Jet streams are usually found near the tropopause, around 9 to 12 kilometers high, though their exact level and shape vary. The polar front jet forms near strong contrasts between cold polar air and warmer mid-latitude air. The subtropical jet is connected partly with poleward moving air from the Hadley circulation and conservation of angular momentum. A jet is not a tube with firm walls. It is a shifting region of strong horizontal wind. Speeds can exceed 200 kilometers per hour and sometimes become much higher. Aircraft flying eastward may gain time from a favorable jet and lose time flying westward against it. The jet also guides weather systems. Disturbances grow near regions where upper-level flow diverges and where temperature gradients provide available energy. A surface cyclone can deepen beneath a favorable jet pattern. Another system can weaken when its upper support disappears. The jet stream rarely follows a perfect latitude circle. It bends into large waves. These are Rossby waves, named after meteorologist Carl Gustav Rossby. Their restoring influence comes from the changing effect of planetary rotation with latitude. Air displaced north or south experiences a different planetary vorticity, and the flow responds by developing wave-like motion. Ridges extend warm air poleward. Troughs carry cold air equatorward. The waves move, amplify, break, and sometimes become blocked. A blocking high is a persistent pattern that slows the ordinary west to east progress of weather. Storms may be diverted around it. Heat can build beneath it. Rain can repeat on one side. Cold air can remain trapped on another. The word blocking does not mean that one solid mass stops the atmosphere. It describes a large-scale arrangement that changes slowly enough to prolong local conditions. This distinction matters when weather feels stuck. A heat wave lasting days is not one parcel of hot air sitting motionless. Air continues moving, sinking, mixing, and exchanging heat. The broad pressure pattern repeatedly favors warming and suppresses relief. The atmosphere maintains a temporary regime. The same global circulation helps produce monsoons. A monsoon is not simply heavy rain. It is a seasonal reversal or major shift in winds associated with changing temperature contrasts between land and ocean and with the migration of tropical circulation. In summer, a continent can heat strongly. Surface pressure falls. Moist air is drawn inland and lifted. Rain increases. In winter, the land cools more quickly. Pressure patterns reverse, and dry continental flow can dominate. The South Asian monsoon is the most famous, but monsoon systems occur in Africa, Australia, the Americas, and East Asia. Mountains intensify some of them by forcing air upward and by heating elevated terrain. Billions of people depend on monsoon timing. A weak season can produce drought and crop failure. An intense burst can produce floods and landslides. The same circulation carries both renewal and risk. Large-scale weather also responds to the ocean. The ocean covers most of Earth's surface and has a far greater heat capacity than the atmosphere. It absorbs energy, transports it through currents, and releases it slowly. Sea surface temperature patterns influence where air rises, where rain forms, and how pressure changes across continents. The most important recurring ocean atmosphere pattern is El Niño Southern Oscillation. Under ordinary tropical Pacific conditions, easterly trade winds help pile warm surface water toward the western Pacific. Cooler water rises near the equator in the east, especially along South America. The atmosphere responds to the warm western water with deep convection and lower pressure. Air rises, flows eastward aloft, descends over the cooler east, and returns as trades near the surface. This coupled circulation is called the Walker circulation. During El Niño, the trades weaken and the central or eastern tropical Pacific becomes unusually warm. Convection shifts eastward. Tropical heating changes the paths of planetary waves and jet streams. Rainfall and temperature patterns change far from the Pacific. During La Niña, the eastern and central Pacific become unusually cool and the ordinary trade wind pattern often strengthens. Neither phase produces identical effects every time. The background climate, season, ocean elsewhere, and exact location of warming matter. El Niño does not directly command each storm. It changes probabilities. Each warm or cool phase eventually passes. The underlying coupled mechanism remains. Weather contains events lasting minutes and patterns lasting seasons. The moving air in our story is now part of both. It follows a local pressure gradient while embedded in trade winds, jet stream waves, and ocean-influenced circulation. Soon it will carry water. That will give the invisible flow a visible form. Water enters the atmosphere molecule by molecule. At the surface of an ocean, lake, wet leaf, soil, or road, liquid molecules are in constant motion. Most remain bound to neighboring molecules. A few near the surface carry enough energy to escape into the air. This is evaporation. The fastest molecules leave preferentially, which is why evaporation cools the remaining liquid. Sweat cools skin for the same reason, provided the vapor can move away. Solar energy drives most global evaporation, especially from the ocean. Wind increases evaporation by replacing moist air near the surface with drier air. Warmth usually increases the number of energetic molecules. Low humidity increases the difference between the amount of vapor present and the amount the air could sustain at saturation. The common phrase warm air holds more water is useful and slightly misleading. Air is not a container with empty spaces waiting to be filled. Water vapor has its own partial pressure. The saturation vapor pressure rises rapidly with temperature because warm liquid water and ice exchange molecules differently with the vapor above them. At a higher temperature, a larger vapor pressure is required for evaporation and condensation to balance. Relative humidity compares the current amount of water vapor with saturation at the same temperature. If the vapor content remains unchanged while air cools, relative humidity rises. When saturation is reached, the temperature is called the dew point. The dew point is therefore closely connected with actual moisture content. A high dew point means much water vapor is present. A low dew point means the air is dry. Relative humidity can be high on a cold morning with little total water vapor and lower on a hot afternoon even though the amount of vapor has changed little. This is why humidity percentages can feel confusing. Dew forms when a surface cools the surrounding air enough for water to condense on it. On a clear night, the ground and objects radiate infrared energy toward the sky. If they cool below the dew point, droplets appear on grass, glass, and metal. If the surface is below freezing, water vapor may deposit as frost or liquid dew may freeze. Cloud formation follows the same saturation principle but usually begins through rising air. As pressure decreases with altitude, a rising parcel expands. Expansion requires work against the surrounding pressure. The parcel's internal energy falls, and it cools. This is adiabatic cooling, a temperature change caused mainly by expansion rather than direct heat exchange with the environment. Unsaturated air cools at roughly 10 degrees Celsius per kilometer under ideal, dry adiabatic conditions. Once condensation begins, latent heat is released and partially offsets the cooling. Saturated ascent therefore cools more slowly, with a rate that varies according to temperature and moisture. This difference is central to atmospheric stability. Imagine lifting a parcel slightly. If it remains warmer and less dense than the surrounding air, it continues rising. The atmosphere is unstable. If it becomes colder and denser than its surroundings, it sinks back. The atmosphere is stable. If conditions lie between, saturation can change the result. A parcel may be stable while dry and become buoyant after enough lifting causes condensation. Meteorologists represent these relationships on diagrams of temperature, pressure, humidity, and altitude. Weather balloons carry instruments through the atmosphere and reveal the profile. From that vertical structure, forecasters estimate cloud bases, instability, freezing levels, and storm potential. The cloud begins only when vapor has somewhere to condense. Pure water vapor can remain supersaturated if no suitable surfaces are present. The atmosphere contains countless aerosol particles: sea salt, dust, smoke, sulfate, organic material, pollen, and pollution. Many act as cloud condensation nuclei. Water molecules collect on them and form droplets. A typical cloud droplet is extremely small, often around 10 micrometers across. It falls so slowly that turbulent motion and gentle updrafts keep it suspended. Billions of droplets together scatter light and make the cloud visible. A cloud is not vapor in the everyday sense. Water vapor is invisible. The visible cloud consists of liquid droplets, ice crystals, or both. Cloud color depends on thickness, illumination, and droplet distribution. A thin cloud scatters sunlight and appears white. A thick cloud blocks light from reaching its base and can look gray or nearly black from below. The darkness does not require dirty water. It often means depth. For centuries, clouds had local and descriptive names without one shared scientific system. In December 1802, a young London pharmacist named Luke Howard presented an essay to the Eskesian Society. Howard was fascinated by forms that changed continuously yet repeated recognizable structures. He proposed Latin names: cumulus for heaped clouds, stratus for layered clouds, cirrus for fibrous, high clouds, nimbus for rain-bearing forms. The names could be combined as clouds changed. Howard's classification was scientific because it allowed observers in different places to describe related structures. It was also poetic enough to influence artists and writers. Johann Wolfgang von Goethe wrote poems in Howard's honor. Painters studied cloud form with new attention. Naming did not freeze the clouds. It made transformation discussable. Modern classification preserves Howard's foundation while adding genera, species, varieties, supplementary features, and accessory clouds. 10 main genera organize the familiar forms. High cirrus clouds consist mostly of ice crystals. Cirrostratus can spread into a veil and produce halos around the sun or moon as light refracts through ice. Altostratus and altocumulus occupy middle levels. Stratus forms broad low layers. Stratocumulus breaks those layers into rolls or cells. Cumulus grows from convection. Cumulonimbus extends through much of the troposphere and contains thunderstorms. The altitude ranges shift with latitude and season. A cloud considered high in a polar atmosphere may occur at an altitude that would be middle level in the tropics. The names describe appearance and level more than one fixed height. A fair weather cumulus often begins where a rising thermal reaches saturation. Sunlight warms patches of ground unevenly. Dark soil, rock, roofs, and fields respond differently. Bubbles or plumes of warmer air rise. At the lifting condensation level, droplets appear. The cloud base looks relatively flat because many thermals reach saturation at a similar altitude. Above the base, the cloud top billows where rising air remains buoyant. Around the edges, environmental air mixes in. Droplets evaporate. The outline changes by the second. The cloud may remain shallow if a stable layer stops ascent. It may deepen if the atmosphere is moist and unstable. A temperature inversion, where temperature increases with height through a layer, strongly resists vertical motion. Inversions can trap low cloud, fog, smoke, and pollution near the surface. They can also cap warm, humid air until enough lifting or daytime heating breaks the restraint, allowing explosive convection. Clouds form through several kinds of lift. Mountains force air upward. Fronts place warm air over denser cold air. Low-level winds converge. Upper-level divergence helps remove air above and encourages ascent below. Tropical heating produces deep convection. Each route leaves a different shape in the sky. On the windward side of a mountain, rising air cools and may produce cloud and precipitation. After crossing the crest, the air descends, compresses, and warms. Relative humidity drops. The leeward side can become warmer and drier, creating a rain shadow. The simplified explanation compares moist ascent with dry descent. Condensation releases heat during the climb, and precipitation removes some water, so the descending air warms rapidly. Real Fein and Chinook winds also depend on mountain waves, mixing, pressure patterns, and air moving around terrain. They can raise temperature dramatically within hours and melt snow quickly. A mountain does not create energy from nothing. It changes the path through pressure and phase. Near coasts, land and water create a smaller circulation. During the day, land usually warms faster than water. Air over land becomes warmer, and the pressure pattern favors an onshore sea breeze near the surface. Air rises over land, returns seaward aloft, and sinks over cooler water. At night, land often cools faster, and a weaker land breeze may reverse the near-surface flow. The sea breeze front can act like a small cold front. It lifts warm inland. The equilibrium vapor pressure over ice is lower than over liquid water at the same sub-freezing temperature. Water vapor, therefore, tends to deposit on ice while nearby supercooled droplets evaporate. The ice crystals grow. This is the Wegener-Bergeron-Fine-Diason process, often shortened to the Bergeron process. Crystals can collide and stick into snowflakes. They can collect supercooled droplets that freeze onto them, producing graupel. They can grow heavy enough to fall. If they pass through air above freezing, they melt and reach the ground as rain. Much mid-latitude rain began as ice. Whether precipitation arrives as rain, snow, sleet, or freezing rain depends on the vertical temperature profile below the cloud. Snow survives if the air remains sufficiently cold. A warm layer aloft can melt snow completely. If a deep cold layer lies beneath, the drops may refreeze into ice pellets before reaching the ground. If the cold layer near the surface is shallow, liquid drops can become supercooled and freeze on roads, trees, and wires. This creates freezing rain. The surface can become coated in clear ice even while the air a short distance above is warmer. A weather forecast that says winter mix is compressing a three-dimensional temperature structure into two words. Snow crystals preserve their own atmospheric histories. Water molecules arrange in a hexagonal ice lattice, giving snow crystals six-fold symmetry. Temperature and supersaturation influence whether growth favors plates, columns, needles, or branching dendrites. The classic broad dendrites often form near about -15 degrees Celsius under moist conditions. As a crystal falls through layers with changing temperature and humidity, each branch experiences nearly the same environment at the same time, so the 6 arms develop related patterns. Tiny differences amplify during growth. Turbulence, collisions, and local vapor fields make exact duplication extraordinarily unlikely. The phrase "no two snowflakes are alike" is not a theorem proven for every crystal that has ever fallen. It expresses the enormous number of possible growth histories. Hail forms differently. A strong thunderstorm updraft carries embryos such as frozen drops or graupel through regions of supercooled water. Liquid freezes onto them. The stones can rise and fall through the storm, collecting layers. Clear ice forms where water spreads before freezing. Cloudy ice forms where droplets freeze quickly and trap air. Eventually, the updraft can no longer support the hailstone, or the stone moves out of the strongest rising current. Large hail therefore reveals powerful storm dynamics. It is not simply rain that froze on the way down. Outside thunderstorms, broad regions of precipitation often belong to mid-latitude cyclones. These weather systems grow where strong horizontal temperature contrasts exist. Warm subtropical air and cold polar air do not sit as two rigid blocks. Their boundary slopes and waves. A disturbance can draw warm air poleward on one side and cold air equatorward on the other. Pressure near the surface begins to fall. Rotation develops. Clouds and precipitation form along fronts. The modern frontal model emerged from the Bergen School of Meteorology in Norway during and after the First World War. Wilhelm Bjerknes had already argued that forecasting should be a problem of physics. If the state of the atmosphere could be observed and the equations governing motion and thermodynamics could be solved, the future state could be calculated. His son Jacob Bjerknes, Halvor Solberg, Tor Bergeron, and colleagues used dense observations around Norway to describe cyclones as waves along boundaries between air masses. They borrowed military language. A front marked the advancing edge of one air mass against another. A cold front occurs where colder, denser air advances beneath warmer air. The slope is relatively steep. Lift can be concentrated. Showers or thunderstorms may form in a narrow band, though some cold fronts produce little weather and others generate broad precipitation. A warm front occurs where warm air advances and rises gradually over retreating cold air. Clouds can appear in sequence far ahead of the surface boundary. High cirrus, thickening layers, then lower cloud, and prolonged rain or snow. An occluded front develops as a faster cold front catches the warm front and lifts the warm sector away from the surface. The textbook life cycle is useful. Real cyclones vary with upper-level waves, moisture, terrain, ocean temperature, and multiple air streams. Some deepen explosively. Some form without a classic surface front. Some decay and then reorganize. The cloud shield seen by satellite is the visible result of air flowing along three-dimensional pathways. Meteorologists sometimes describe warm conveyor belts, cold conveyor belts, and dry intrusions. A warm conveyor belt carries moist air upward ahead of the cold front and over the warm front, producing broad cloud and precipitation. A dry intrusion descends from upper levels and can create the clear slot seen curling into mature cyclones. The comma shape on a weather image is a map of moving air. Pressure at the center does not pull clouds like a drain. The cyclone is a coupled circulation maintained by temperature contrasts, upper-level dynamics, latent heat, and friction. As warm and cold air exchange positions, available potential energy becomes kinetic energy. The system helps transport heat poleward. Storms are one way the atmosphere reduces the gradient that creates them. The reduction never finishes because solar heating continues. A cyclone crossing an ocean can also become linked with an atmospheric river. Atmospheric rivers are long, narrow corridors of strong water vapor transport, usually concentrated in the lower troposphere. They are not rivers of liquid suspended in air. Their name describes the amount and organization of vapor carried by wind. An average atmospheric river can transport water vapor at a rate comparable to the average flow of the Mississippi River at its mouth. Strong events can carry many times that amount. Most of the water remains invisible until lift occurs. When the corridor reaches a coast and encounters mountains, air rises, cools, and condenses. Rain or snow can become intense and persistent. Atmospheric rivers are not inherently disasters. They supply major portions of annual water in regions such as Western North America. Reservoirs and mountain snowpack depend on them. Weak and moderate events are beneficial. Strong, slow, or repeated events can produce floods, landslides, erosion, and rain on snow hazards. One feature can be both water supply and extreme weather. The same is true of fronts. A front can end drought, refill rivers, clear pollution, damage crops, or produce severe storms depending on timing and strength. Weather categories describe mechanisms. Impact depends on the place they meet. The cloud in our story has entered a lifting region within a cyclone. Droplets and ice crystals grow. Some begin falling. The descending precipitation pulls air with it and cools surrounding air through evaporation and melting. A downdraft forms. If the cloud is shallow, the rain may reach the surface quietly. If the atmosphere contains greater instability, moisture, and wind shear, the same basic ingredients can build something taller. The cloud can become a thunderstorm. A thunderstorm requires three broad ingredients: moisture, instability, a way to lift air. Wind shear is not required for every thunderstorm, but it determines whether a storm remains a brief pulse or organizes into a longer-lived system. The first stage can look harmless. Warm, humid air rises in a developing cumulus cloud. Condensation releases latent heat, helping the rising parcel remain warmer than its environment. The updraft strengthens. Cloud droplets, ice crystals, and graupel grow. The top climbs through colder layers. A vigorous tropical storm can reach beyond 16 kilometers. In mid-latitudes, the tropopause is often lower. When the rising air reaches a stable layer near the tropopause, it spreads horizontally into an anvil. Overshooting tops can briefly rise above the anvil where the strongest updraft carries momentum into the stable air. At first, almost all motion inside the cloud may be upward. Then precipitation becomes heavy enough to fall. Evaporation, melting, and drag cool and pull air downward. A downdraft develops. When the downdraft reaches the ground, it spreads outward as a gust front. The leading edge can lift warm air and create new cells. A simple single-cell storm often weakens when its downdraft cuts off the warm, moist inflow feeding the updraft. Organized storms survive by separating rising and descending currents. Wind shear can create that separation. If wind speed increases with height, precipitation falls downwind of the updraft. If wind direction also changes with height, the storm can acquire rotation. Multi-cell clusters, squall lines, mesoscale convective systems, and supercells are different ways convection organizes. A squall line can stretch hundreds of kilometers and produce widespread damaging wind. A mesoscale convective system can continue through the night, supported by low-level moisture transport and cold pools generated by previous storms. A supercell contains a persistent rotating updraft called a mesocyclone. The rotation begins partly with horizontal tubes of spin produced by vertical wind shear. The storm's updraft tilts some of that rotation toward the vertical and stretches it. Stretching a rotating column can increase its spin, as a skater turns faster when drawing in the arms. The analogy helps, but a supercell is not one smooth tube. Pressure perturbations, precipitation, temperature gradients, downdrafts, and changing inflow interact across scales. The storm can contain a broad rotating region several kilometers wide, while any tornado beneath it is far narrower. Lightning begins inside the mixed-phase region. Collisions among small ice crystals, graupel, and supercooled droplets transfer electrical charge. The exact sign depends on temperature, liquid water content, collision conditions, and particle type. A common pattern leaves small ice crystals positively charged and carried upward, while heavier graupel gains negative charge and remains lower. Other charge layers also form. The cloud becomes electrically separated. The electric field strengthens between regions inside the cloud, between clouds, and between cloud and ground. Air normally resists current. A lightning discharge develops when the field and local ionization create a conducting path. The process occurs in stages. A stepped leader can advance from cloud toward ground in branches too faint and fast for ordinary sight. Positive streamers rise from objects below. When connection occurs, a powerful return stroke travels along the channel. The bright flash seen as one bolt may contain several strokes following related paths. Most lightning occurs within clouds. Cloud-to-ground flashes are only one part of a storm's electrical activity. Positive cloud-to-ground lightning can originate from higher positive regions and strike far from the rain core. These flashes can carry strong currents and reach areas under blue sky. The safest rule remains simple. If thunder can be heard, lightning is close enough to be dangerous. A lightning channel heats surrounding air to around 30,000 degrees Celsius in a fraction of a second. The air expands explosively and launches a pressure wave. Nearby, thunder begins as a crack or bang. Farther away, it becomes a rumble because sound from different parts of the long channel travels different distances and is refracted and reflected through the atmosphere and terrain. Light arrives almost instantly on human scales. Sound travels much more slowly. Counting seconds between flash and thunder gives a rough distance, about 3 seconds per kilometer or 5 seconds per mile. The electrical nature of lightning was debated long before anyone could observe the charge structure of a cloud. Benjamin Franklin proposed that pointed metal conductors might draw charge and protect buildings. His famous kite experiment is often retold as Franklin flying directly into a lightning strike. That would likely have killed him. In 1752, Franklin used a wet kite line during a storm and observed electrical charge collect on a key, demonstrating that storm clouds were electrified. Similar experiments were dangerous, and at least one researcher, George Wilhelm Richmond, was killed while investigating atmospheric electricity. The practical result was the lightning rod. A rod does not create a protective bubble by draining every storm cloud. It provides a preferred attachment point and a low-resistance path that conducts current toward ground through a system designed to handle it. Protection depends on the whole installation: air terminals, conductors, bonding, and grounding. The rod does not repel weather. It gives electricity a safer route. Lightning can also initiate fires, damage electronics, injure nerves, and produce shock waves. It fixes atmospheric nitrogen into chemically reactive forms, contributing to the nitrogen cycle. A single phenomenon can be hazard in planetary chemistry. The thunderstorm's downdraft produces another danger. When a concentrated column of air descends and spreads outward at the surface, it can create a downburst. A microburst affects a relatively small area but can produce destructive straight-line winds and rapid changes of direction. Aircraft near the ground are especially vulnerable because an approaching plane may first gain airspeed and headwind, then encounter sinking air and a sudden tailwind that reduces lift. Research into microbursts transformed aviation forecasting and radar. In the 1970s, meteorologist Tetsuya Theodore Fujita studied aircraft accidents, storm damage, and aerial photographs. He identified intense localized outflows and developed the term downburst. Fujita also created the tornado damage scale that carried his name. The original Fujita scale linked observed damage with estimated wind ranges from F0 to F5. In 2007, the United States adopted the enhanced Fujita scale. The EF scale uses damage indicators and degrees of damage for buildings, trees, and structures to estimate the winds likely required. This means a tornado rating is not normally a direct anemometer measurement. A violent tornado crossing an empty field may leave too little engineered damage for a confident highest rating. A poorly built structure can be destroyed at lower winds than a well-built one. The scale measures damage as evidence for wind. It does not measure the complete vortex. Mobile Doppler radar has observed extreme winds in some tornadoes, but measurements occur at particular heights, distances, and moments. The strongest velocity near the ground may never intersect an instrument. Claims of exact maximum wind should therefore be treated cautiously. Tornado formation remains one of meteorology's hardest problems. Many supercells rotate. Only some produce tornadoes. Even storms with apparently favorable environments can fail, while another nearby storm develops a vortex. The broad ingredients include instability, moisture, lift, and vertical wind shear. Near the ground, temperature and moisture differences created by rain-cooled downdrafts can generate and concentrate rotation. The balance is delicate. A downdraft that is too cold may undercut the updraft. One that is too weak may fail to bring rotation downward. Terrain, storm interactions, boundary collisions, and internal pressure changes can alter the outcome. A tornado may begin when rotation near the surface is intensified and connected with the storm above, but researchers continue debating the sequence in different cases. There may not be one universal pathway. Tornado Alley is a useful cultural name and an incomplete map. The central United States often combines moist Gulf air, elevated dry air, strong temperature contrasts, and powerful shear. Yet tornadoes occur across much of the country and on every continent except Antarctica. Their regional patterns vary by season. Parts of South America, Bangladesh, South Africa, Europe, Australia, and other regions experience significant tornadoes. The United States reports many partly because geography favors them and because observation and documentation are extensive. Climate change adds uncertainty. A warmer atmosphere can hold more water vapor and may increase instability in some environments. Changes in shear may oppose or reinforce that effect depending on region and season. Observed tornado records are complicated by changing population, reporting, radar, and damage assessment. Scientists have stronger confidence in increasing heavy rainfall and heat extremes than in global trends for tornado frequency. The appropriate answer is not that climate has no influence. It is that small, short-lived vortices are difficult to observe consistently and emerge from competing ingredients. Inside a tornado, pressure falls and wind accelerates around the vortex. The visible funnel consists of condensed droplets and debris, not the rotating air itself. A circulation can reach the ground before a visible funnel does. A funnel can remain aloft without becoming a tornado. The safest identification comes from radar, trained observation, and evidence of contact with the surface. The storm in our story does not need to produce one. Most thunderstorms do not. Its charge discharges through the cloud. Rain falls. The gust front passes. Energy that began as sunlight and evaporation is being released through motion, condensation, sound, and heat. Over warm tropical water, however, organized thunderstorms can join a much larger engine. The result is not a larger tornado. It is a tropical cyclone. A tropical cyclone begins with ordinary convection over warm water. Many disturbances never organize. The ocean must be warmed through enough depth to supply energy without being cooled immediately by mixing. The lower atmosphere must contain moisture. Winds at different heights must not tear the developing circulation apart. The system must be far enough from the equator for planetary rotation to help organize spin. A pre-existing disturbance is usually present. It may be a tropical wave moving westward from Africa, a decaying front, a monsoon trough, or another region of organized thunderstorms. Warm water evaporates. Air near the surface gains moisture and enthalpy, the combined energy associated with temperature and water vapor. Convection lifts the air. Vapor condenses and releases latent heat. The warming aloft lowers density in the column and helps pressure fall at the surface. Lower pressure strengthens inward flow. The inward wind increases evaporation and feeds more moisture toward the storms. If the circulation remains organized, a feedback develops. The system is a heat engine, but not one operating between a boiler and a piston. It extracts energy from the warm ocean and releases heat in the cold upper troposphere. The outflow spreads high above the storm. Near the surface, air spirals inward. In the eye wall, it rises rapidly. At the center of a mature cyclone, some air descends and warms, suppressing cloud and creating the eye. The eye can be strikingly calm compared with the eye wall around it. Pressure is lowest near the center. Winds are not necessarily strongest there because the small pressure gradient inside the eye and descending air create a different structure. The strongest sustained winds usually occur in the eye wall, where the pressure changes rapidly across distance and deep convection is concentrated. An eye is not empty. Low cloud can swirl inside. Mesovortices can form along the eye wall. The sea beneath remains violent. The eye can shrink, expand, wobble, or disappear as the storm changes. In intense cyclones, a second ring of thunderstorms may form outside the original eye wall. The outer ring competes for moisture and angular momentum. The inner eye wall weakens, and the outer one contracts. This eye wall replacement cycle often reduces peak wind temporarily while expanding the area of strong wind. The cyclone can intensify again afterward. Forecasting intensity is difficult partly because these internal reorganizations occur on scales smaller than the whole storm. Tropical cyclones are called hurricanes in the North Atlantic and eastern North Pacific, typhoons in the western North Pacific, and cyclones in several other basins. The physical phenomenon is the same. Naming conventions and wind thresholds differ among agencies and regions. A tropical depression has an organized circulation with lower winds. A tropical storm receives a name. A hurricane or typhoon crosses the regional intensity threshold. Categories describe maximum sustained wind. They do not describe every hazard. A category can weaken before landfall while carrying enormous water. A compact intense storm may produce less widespread wind than a large lower category 1. Storm surge, rainfall, waves, tornadoes, and inland flooding can kill far from the point where the center crosses the coast. Storm surge occurs when wind pushes seawater toward shore and low pressure contributes a smaller rise. The shape of the seabed and coastline can amplify the water. A shallow continental shelf allows surge to build. A bay can funnel it. Tide adds or subtracts from the total level. Waves ride on top. The result is not simply a higher tide. It is moving ocean entering places built for land. Rainfall depends on storm speed, moisture, terrain, and interaction with other weather systems. A slow tropical cyclone can produce catastrophic flooding even after winds weaken. Warm tropical air can hold abundant vapor. Convergence and repeated rain bands deliver it to the same watershed. Mountains force additional lift. Rivers rise after the center has moved away. The most damaging part of a hurricane can therefore arrive after the dramatic satellite image has begun fading. The energy of a tropical cyclone is often compared with bombs or the electricity used by civilization. Such comparisons can mislead. The storm releases an enormous amount of latent heat as water condenses. Only a small fraction becomes the kinetic energy of wind. The destructive power near the surface depends on that kinetic energy, water movement, waves, rainfall, duration, and where the storm travels. Equating all condensation heat with usable electrical power suggests a machine that does not exist. The meaningful fact is simpler. A hurricane operates by processing ocean heat and water vapor across an area larger than many countries. No human device can control that flow. Humans can observe, forecast, prepare, and build for it. The cost of not seeing a cyclone clearly became unforgettable at Galveston. At the beginning of September 1900, a hurricane crossed the Caribbean and entered the Gulf of Mexico. Forecasters knew that a storm existed, but its future track remained uncertain. Ships in the Gulf encountered dangerous conditions, yet wireless ship-to-shore communication was not available to send their observations quickly. Galveston, Texas, was a prosperous island city whose highest natural ground stood less than 3 meters above sea level. The sea had crossed parts of the island during previous storms, but the scale of the approaching surge was not understood. On September 8, long ocean swells reached the coast. Water began rising around the city. Wind strengthened. Telegraph and transport links failed. The local anemometer was destroyed before the strongest wind arrived. The hurricane came ashore with what modern reconstruction classifies as Category 4 intensity. Water rose more than 4 meters above ordinary level in places and crossed nearly the entire island. Buildings failed under wind, waves, and floating debris. At least several thousand people died, and the event remains the deadliest natural disaster in United States history. The catastrophe is sometimes told as the failure of one forecaster. That is too simple. The observing network over the ocean was incomplete. Communication was slow. Hurricane structure and storm surge were poorly understood. Forecast authority and international exchange were limited. The city itself was exceptionally exposed. A warning can only be as useful as the information, institutions, and physical protection around it. Galveston rebuilt. Engineers constructed a seawall. Large portions of the city were raised by lifting buildings and adding sand beneath streets and foundations. When another powerful hurricane struck in 1915, the seawall did not prevent every flood or death, but it greatly reduced devastation in the protected part of the city. The atmosphere had not become gentler. Observation, warning, and engineering had changed what the weather could do to the population. The lesson reaches beyond hurricanes. A forecast is one layer of safety. The shape of a coast, the height of a house, the strength of a roof, the route of evacuation, and the ability to receive a warning determine the rest. Meteorology predicts a hazard. Society determines how much of that hazard becomes disaster. Modern surge forecasting, therefore, uses more than the hurricane's category. Models combine the storm's size, speed, track, pressure, and wind field with tides, coastline shape, seafloor depth, rivers, and elevation. Two storms with similar maximum wind can push very different amounts of water onto land. A forecast map can show water depth above ground rather than only distance from the coast. This is another example of weather becoming useful only when physics meets place. The atmosphere supplies the wind. The ocean and coastline determine how the water responds. Roads, buildings, warnings, and evacuation determine who remains exposed. Observation transformed tropical cyclone science. Before satellites, a storm over the open ocean could remain unknown until a ship encountered it or it neared land. Ships provided pressure, wind, cloud, and wave reports at great risk. Coastal telegraph networks allowed warnings to move faster than storms. Aircraft reconnaissance began during the Second World War after military pilots flew into tropical cyclones, first by circumstance and then deliberately. Modern hurricane hunter aircraft cross the storm repeatedly. They measure wind, pressure, temperature, humidity, and radar structure. Instruments called dropsondes are released and transmit data while falling beneath parachutes. The aircraft does not fly through weather untouched. Turbulence moves the airframe. Ice and precipitation strike it. Crews follow carefully designed routes. The data enter forecast models and help determine the center, intensity, and wind field. Satellites observe clouds, water vapor, temperature, lightning, sea state, and microwave signatures through much of the storm. Scatterometers estimate ocean surface wind from radar reflections. Ocean floats and gliders measure heat below the surface. A cyclone can intensify over a deep reservoir of warm water and weaken when its own winds mix colder water upward. The ocean under the storm is not a flat temperature map. Eddies, currents, salinity, and depth matter. Climate change alters the background. The ocean has absorbed most of the excess heat added to Earth's climate system. Warmer air can contain more water vapor. Sea level is higher, allowing storm surge to reach farther inland from the same meteorological forcing. Evidence indicates that human-caused warming increases heavy precipitation associated with tropical cyclones. The proportion of storms reaching high intensity is expected to rise globally, even though changes in total storm number are less certain and vary by basin. Rapid intensification is a growing concern because warm water, moist air, and favorable winds can allow maximum winds to increase quickly near a coast. One storm cannot be attributed to climate change merely because it was severe. Attribution compares the event's probability or intensity in the present climate with a modeled world without the human influence. Climate change loads some parts of the weather system without scripting each exact path. Tropical cyclones also cool the ocean beneath them, redistribute heat, mix nutrients, damage forests, open gaps in ecosystems, and carry rain into dry regions. They are not foreign objects invading climate. They are part of the climate system, made hazardous where human lives and structures meet them. The cyclone in our story remains over water. Its clouds spiral. The eye breathes through cycles. Rain bands carry moisture outward. Eventually, cooler water, dry air, land, or strong wind shear disrupts the engine. The circulation weakens. Its moisture can continue poleward and merge with a mid-latitude front, producing rain far from the tropics. A storm does not always end where its name disappears. Its energy and water enter the next weather system. Not every important weather system is large. A valley can create its own night. A city can remain warmer than surrounding fields. A lake can generate snow. A forest can add moisture to the air and change how sunlight reaches the ground. Local weather begins where the broad atmosphere meets a particular surface. During a clear, calm night, the ground emits infrared radiation and cools. The air touching it cools by conduction and mixing. Because cold air is dense, it drains downslope and collects in low terrain. A valley floor can become colder than hillsides above it. This is a temperature inversion. Colder air lies beneath warmer air, reversing the usual decrease of temperature with height. The inversion suppresses mixing. Smoke, vehicle emissions, and moisture remain trapped near the surface. Fog can form if the air reaches saturation. Radiation fog often develops in this way. It is most likely when the night is clear enough for strong cooling, the wind light enough to avoid mixing, but not always perfectly calm, and moisture available near the ground. After sunrise, heating and turbulence can mix the layer and evaporate the droplets. The fog appears to lift because the lowest portion may warm and disappear first, leaving a temporary cloud deck above. Advection fog forms when moist air moves over a colder surface. Along the California coast, relatively cool ocean water helps chill marine air. Winds can carry fog through the Golden Gate and into San Francisco, while nearby inland areas remain clear and hot. Sea fog forms over cold currents and melting ice. Upslope fog forms when air is forced gradually uphill and cools. Steam fog appears when cold air moves over warmer water, adding vapor that condenses almost immediately into shallow wisps. Fog is a cloud in contact with the surface. The formal visibility threshold varies slightly by observing practice, but meteorological fog generally reduces horizontal visibility below 1 kilometer. Mist is thinner. The distinction sounds tidy until visibility changes from one road bend to the next. Fog droplets scatter light. High beams can worsen visibility by returning glare toward a driver. Sound travels in complex ways because temperature profiles refract it. Fog can quiet a landscape visually while making distance harder to judge. It has shaped ports, battles, aviation, and urban history. London's old pea soup fogs combine natural fog with smoke and sulfur from coal. The Great Smog of December 1952 formed under a persistent inversion. Pollution accumulated for days. Visibility collapsed, transport stopped, and thousands of excess deaths occurred, with later estimates extending higher. The event helped produce stronger clean air legislation. What appeared to be weather was also fuel, industry, housing, and public policy. The atmosphere does not distinguish natural particles from human ones when droplets form on them. Cities modify weather in several ways. Dark roofs and pavement absorb sunlight. Buildings store heat in walls and release it slowly after sunset. Impermeable surfaces reduce evaporation. Vehicles, cooling systems, people, and industry release waste heat. Street canyons alter wind and trap radiation. The result is the urban heat island. It is often strongest at night, when rural surfaces cool rapidly while the city releases stored heat. The difference varies with city design, season, wind, cloud, vegetation, and neighborhood. An average urban heat island value can hide large inequality. Tree-lined areas may remain cooler. Dense districts with little shade can become much hotter. Top-floor apartments store heat. Air conditioning protects indoor spaces while releasing heat outdoors and increasing electricity demand. During a heat wave, the urban island adds to the larger weather pattern. Heat waves are among the deadliest weather hazards because they can persist, affect wide areas, and cause illness without dramatic visible damage. The human body cools through sweating and increased skin blood flow. When humidity is high, evaporation becomes less effective. When nighttime temperatures remain high, the body receives less relief. Age, medication, illness, housing, work, and access to cooling change risk. Temperature alone does not define heat stress. Wet bulb temperature combines heat and humidity by measuring the cooling possible through evaporation from a wet surface. Simplified claims sometimes state that one exact wet bulb threshold marks universal human survival. Laboratory and physiological studies show that dangerous limits vary with activity, wind, sunlight, acclimatization, age, and health, and can occur below the theoretical maximum often quoted. Weather impacts bodies through context. Cold operates the same way. A thermometer may read one value while wind increases convective heat loss from exposed skin. Wind chill expresses how cold conditions feel relative to a calm reference under standardized assumptions. It does not mean objects cool below the actual air temperature solely because of wind. Wind makes them reach the air temperature faster. Snow cover transforms local weather. Fresh snow reflects much of the sunlight that would otherwise warm the ground. It insulates soil beneath. It cools air above through radiation and melting. The bright surface can maintain cold conditions after the storm has passed. Forests interrupt this effect by absorbing sunlight in dark canopies and sheltering snow from wind. Cities remove snow quickly from roads and produce heat that changes accumulation. A weather map may show one air mass. The surface breaks it into many microclimates. Large lakes create another. In autumn and early winter, Cold air moving across relatively warm, unfrozen water gains heat and moisture from below. Convection develops in bands aligned with the wind. When the air reaches the downwind shore and rises over terrain, snow intensifies. Lake effect snow can create narrow regions of extreme accumulation, while locations a few kilometers away receive little. As the lake freezes, moisture and heat flux decline. The shape of the shoreline, wind direction, fetch, instability, and topography determine where the bands form. The same principle produces ocean effect snow near other coasts. Mountains create local waves in air. Stable flow crossing a ridge can oscillate vertically, like water moving over a submerged rock. Lenticular clouds form near wave crests where rising air cools to saturation and disappear where descending air warms. They appear stationary while air moves rapidly through them. Rotors can form beneath the waves and create severe turbulence. A smooth lens-shaped cloud may therefore mark violent, invisible motion. Pilots learn to read clouds as evidence of flow. People have done this long before formal meteorology. Sailors watched halo rings, cloud sequences, swell direction, and pressure. Farmers observed wind shifts, animal behavior, dew, and sky color. Mountain communities learn the clouds associated with terrain. Some traditional signs contain physical relationships. A red evening sky in the mid-latitudes can occur when clear dry air lies to the west and low-angle sunlight illuminates clouds toward the east, consistent with approaching fair weather under ordinary west-to-east flow. The rhyme is not universal. Tropical circulation, pollution, local cloud, and different storm tracks can reverse the implication. A halo around the moon can indicate high ice clouds arriving ahead of a warm front. It does not guarantee rain. Weather lore works when repeated local observation captures a real pattern. It fails when the pattern is exported beyond the conditions that created it. Modern instruments extend those senses. A thermometer measures temperature. A barometer measures pressure. A hygrometer estimates humidity. An anemometer measures wind speed, while a vane gives direction. A rain gauge catches precipitation at one point. Each measurement has exposure requirements. A thermometer against a sunny wall measures the wall's environment, not standardized air temperature. A rain gauge beneath a tree misses water and receives drips. An anemometer among buildings measures turbulence created by buildings. Weather observations are not just numbers. They are numbers tied to instrument, height, shielding, location, and time. The standard screen once used widely for thermometers is called a Stevenson screen. Its white slatted box shades instruments while allowing air to circulate. Modern automated stations use electronic sensors and radiation shields, but the principle remains. Measure the atmosphere without letting the instrument's surroundings dominate. Even a careful station observes one point. A shower can pass between gauges. A gust can occur between reporting intervals. A valley station cannot represent a mountain summit. Forecasting required observations from many places at the same time. Before fast communication, that was impossible. A report from a distant coast arrived after the weather had already moved. The telegraph changed the relationship between weather and distance. For the first time, observations could travel faster than a storm. In the middle of the 19th century, weather prediction was still viewed with suspicion. Astronomy could forecast an eclipse because celestial motion followed regular paths. Weather changed, failed, and embarrassed anyone who claimed certainty. The word forecast itself was not yet ordinary in this context. Robert Fitzroy helped make it so. Fitzroy had commanded HMS Beagle during the voyage that carried Charles Darwin around the world. He was an experienced sailor and observer of pressure, wind, sea, and cloud. In 1854, he became head of the British Meteorological Department within the Board of Trade. The first task was not public forecasting. It was collecting marine observations. Ships and coastal stations measured pressure, wind, temperature, and weather. The telegraph allowed reports from different coasts to reach London quickly enough to be drawn on one chart. This was synoptic meteorology, viewing the atmosphere at one time across a broad region. The word synoptic means seen together. A falling barometer in one harbor meant little by itself. A pattern of falling pressure, changing wind, and moving cloud across several stations revealed a storm. In October 1859, a violent cyclone crossed the British Isles. The steam clipper Royal Charter was driven onto rocks near Anglesey and broke apart. Around 460 people died. Many other vessels were lost in the same gale. Fitzroy studied the observations and argued that warnings could have been issued before the storm arrived. In February 1861, the Meteorological Department began a storm warning service. Coastal stations raised cones and drums to show expected wind direction and danger. A shape on a mast carried information to ships beyond the reach of immediate text. Later that year, Fitzroy began publishing public forecasts. The first appeared for the end of July and beginning of August 1861. The reports were brief and regional. Forecasting created political risk. A mist storm brought criticism. A warning that proved unnecessary disrupted trade. Scientific opponents argued that the atmosphere could not be predicted reliably. After Fitzroy's death in 1865, official forecasting was suspended temporarily. Public pressure and parliamentary concern helped restore storm warnings. The service survived because people had seen that imperfect warning could still save lives. Forecasts would remain probabilistic even when their language sounded definite. Fitzroy's work also carried personal strain. He faced relentless criticism, financial pressure, and severe depression, and died by suicide. His story should not be romanticized as the lonely genius defeated by skeptics. Forecasting grew through networks of observers, telegraph operators, sailors, instrument makers, mathematicians, and governments. Fitzroy's role was to insist that simultaneous observations could become practical warning. The weather map had become a form of public safety. Other countries developed related services. The United States organized national weather observations after the Civil War, initially through the Army Signal Service. Telegraph reports were assembled into maps and bulletins. International cooperation became necessary because storms crossed borders without permission. Ships standardized observations. Governments exchanged data. Timekeeping improved. Instruments became comparable. The atmosphere had always been global. Meteorology had to become global to observe it. Surface stations still could not reveal the vertical atmosphere. Kites carried instruments upward. Mountain observatories measured higher levels. Piloted and unmanned balloons reached farther. In the 1890s, instrument packages attached to balloons recorded temperature, pressure, and humidity. The discovery of the stratosphere came from such measurements. Léon Tisserand de Bord in France and Richard Assmann in Germany found that temperature stopped decreasing and began behaving differently above the troposphere. The upper atmosphere was not a simple continuation of surface cooling. Radiosondes later transmitted measurements by radio while rising beneath weather balloons. Twice each day, stations around the world still launched them at coordinated times, with additional launches during significant weather. A radiosonde can climb beyond 30 kilometers before the balloon bursts. Its path also reveals wind as the package is tracked. One vertical profile can determine whether thunderstorms are likely, whether freezing rain can form, or how much energy is available to convection. The balloon's data enter a global model within hours. Weather radar added another sense. Radar sends radio waves and measures energy scattered back by targets. During the Second World War, operators noticed unwanted echoes from rain and snow. The interference became information. Modern Doppler weather radar estimates where precipitation exists and how particles move toward or away from the instrument. Reflectivity relates imperfectly to particle size and concentration. Velocity reveals motion along the radar beam. Rotation can appear as adjacent regions moving toward and away from the radar. Dual polarization radar sends waves in horizontal and vertical orientations, helping distinguish rain, snow, hail, insects, and debris by their shapes and behavior. A tornado debris signature can confirm that a damaging vortex is lofting material. Radar does not see every storm perfectly. Earth's curvature carries the beam higher above ground with distance. Mountains block it. Temperature inversions bend the beam unusually. Heavy rain can attenuate some wavelengths. Velocity is measured only along the beam, not as a complete three-dimensional wind. He divided the atmosphere into a grid and attempted to solve approximate equations step by step. The calculation took weeks or months of work for a forecast interval of hours. The predicted pressure change was wildly unrealistic. The failure came partly from noisy initial data and fast atmospheric waves that the calculation did not handle properly. Richardson did not abandon the idea. In his 1922 book Weather Prediction by Numerical Process, he imagined a forecast factory shaped like a vast theater. Thousands of human calculators would occupy tiers, each responsible for part of the globe. A conductor would coordinate the work. Signals would carry numbers between sections quickly enough for the forecast to stay ahead of weather. The image was impossible in its time. Its architecture resembled parallel computing. The weather factory waited for electronics. In 1944, weather forecasting entered a room where one decision could affect thousands of lives. The Allied invasion of Normandy required more than military readiness. Landing craft had to cross the English Channel. Aircraft needed ceilings and visibility. Wind and waves had to remain manageable. Tides had to expose beach obstacles and then rise behind the arriving troops. Moonlight mattered to airborne operations. Only a few dates offered a suitable combination. The invasion was planned for June 5. Group Captain James Stagg served as chief meteorological advisor to General Dwight D. Eisenhower. Stagg did not make the forecast alone. He had to reconcile teams from the British Met Office, the Royal Navy, and the United States Army Air Forces, whose interpretations did not always agree. The observing network was sparse by modern standards. There were no weather satellites. No Doppler radar crossed the Atlantic. No global numerical model assembled the atmosphere into one analysis. Forecasters relied on ships, aircraft, coastal stations, pressure charts, upper air reports, and experience with North Atlantic storms. One of the most valuable stations stood at Blacksod Point on the western edge of Ireland. During the early hours of June 3, Maureen Flavin, a 21-year-old postal clerk who also took weather observations, recorded falling pressure, strengthening wind, rain, and drizzle. Ireland was neutral, but weather observations were shared with Britain. The readings mattered because systems approaching Europe from the Atlantic often reached Blacksod before most other land stations. Officials asked for the observation to be checked. The pressure was still falling. The report supported the British concern that stormy weather would reach the Channel on June 5. Stagg advised Eisenhower that the planned day was too dangerous. Postponement carried its own risk. Thousands of ships and aircraft were already assembled. Soldiers had been briefed. Secrecy could not be preserved indefinitely. The next suitable combination of tides and moon would not arrive immediately. Eisenhower delayed the operation by 24 hours. Then the atmosphere changed just enough. Observations showed pressure beginning to rise behind a front. Stagg and the forecasting teams identified a short interval of improved, though far from perfect, conditions on June 6. Rain, low cloud, wind, and rough water would still affect the operation. The forecast did not promise calm. It identified a temporary window less dangerous than the storm surrounding it. Eisenhower gave the order to proceed. The poor weather also influenced the opposing side. Some German commanders considered a major invasion unlikely under such conditions. Later in June, another severe storm struck the channel and damaged the artificial harbors supporting the landing. The narrow forecast window had mattered. The story is sometimes simplified into one heroic meteorologist predicting D-Day. The real achievement was collective. An observer at a remote lighthouse measured pressure accurately. Telephone and telegraph moved the report. Several forecasting groups interpreted incomplete data. Stagg translated disagreement and uncertainty into advice. A commander decided what level of risk could be accepted. The forecast was not perfectly correct in every local detail. It was useful enough at the scale of the decision. That is still the purpose of operational meteorology. A forecast does not need to remove uncertainty before it can change history. Electronic computing turned Richardson's impossible theater into an engineering problem. During the late 1940s, mathematician John von Neumann and meteorologist Jules Charny worked with colleagues to simplify the atmospheric equations enough for an early computer. The machine was ENIAC. It filled a room, used thousands of vacuum tubes, and had far less computing power than a modern phone. Charny removed fast atmospheric waves that had overwhelmed Richardson's hand forecast and focused on large-scale motion. In 1950, Charny, Ragnar Fjortoft, von Neumann, and their team produced numerical forecasts of the evolution of a mid-tropospheric pressure pattern. A 24-hour forecast required roughly a day of machine time. The forecast could barely keep pace with the atmosphere. It was still a threshold. Weather had been advanced through equations on an electronic computer. Operational numerical prediction followed as machines improved. Early models represented only broad patterns. Grid points were far apart. Mountains were smoothed. Clouds and turbulence could not be calculated explicitly. Processes smaller than the grid had to be parameterized, represented through equations describing their average effects. Modern global models resolve much finer scales, but parameterization remains necessary. A cloud droplet is smaller than a model grid cell by enormous factors. Turbulent eddies exist below resolution. Soil, vegetation, waves, radiation, and convection interact across scales. Higher resolution moves the boundary. It does not remove it. A numerical model divides the atmosphere into a three-dimensional grid or mesh. At each step, equations update wind, temperature, pressure, moisture, cloud, precipitation, and other variables. The time step must be short enough to maintain numerical stability and represent fast processes. The model exchanges energy and water with land, ocean, and ice. Radiation enters and leaves. Friction acts. Clouds form. Precipitation reaches the ground. The simulation advances millions or billions of calculations at once. Errors come from several sources. The initial atmosphere is imperfectly observed. The equations are approximated on a grid. Subgrid processes are parameterized. The ocean and land state may contain errors. Computers use finite precision. A single forecast cannot reveal how those uncertainties affect the outcome. Ensemble forecasting addresses this problem. Instead of running one model once, centers run many forecasts with slightly different initial states, model formulations, or both. If the members remain close, confidence is higher. If they diverge, the atmosphere is in a less predictable configuration. An ensemble does not produce several random guesses. The perturbations are designed to represent plausible uncertainty. The output becomes probability. A 30% chance of rain does not mean it will rain for 30% of the day or over exactly 30% of a city in every case. The precise operational meaning depends on the forecast system, but it generally represents the probability of measurable precipitation at a location or within an area during a period. People often hear probability as indecision. In a chaotic system, Probability is more honest information than false certainty. A deterministic icon can hide the range of possible outcomes. A forecast cone for a tropical cyclone offers another example. The cone represents uncertainty in the track of the center based on historical errors. It does not show the full size of the storm. Hazardous wind, rain, surge, and tornadoes can occur outside it. The cone usually widens with time because uncertainty grows. The center does not have equal probability everywhere inside the shape, and impacts do not stop at the boundary. A graphic designed to simplify uncertainty can create new misunderstanding. Forecast skill has improved dramatically. A useful forecast several days ahead today is often more accurate than a much shorter forecast was decades ago. Improvement comes from satellites, radar, aircraft data, better models, data assimilation, faster computers, ensemble prediction, and better understanding of physical processes. The statement that forecast skill gains roughly a day per decade is a broad historical summary, not a law that will continue unchanged. Different variables improve at different rates. Large-scale pressure is more predictable than the exact location of a summer thunderstorm. Temperature over a broad region may be skillful farther ahead than whether one street receives hail. Some predictive information extends beyond 10 days, especially for large-scale regimes, tropical waves, sudden stratospheric changes, or seasonal patterns. Detailed deterministic weather loses skill much sooner. The atmosphere does not have one universal expiration date for every forecast. Edward Lorenz revealed why. Lorenz was a meteorologist at the Massachusetts Institute of Technology. In the early 1960s, he used a computer to explore simplified atmospheric convection. According to the famous account, he wanted to repeat part of a simulation. Instead of beginning from the original data stored in the machine, he typed values printed on paper. The printed numbers had been rounded. A value such as 0.506127 was entered as 0.506. The difference seemed tiny. At first, the repeated simulation followed the original. Then the paths separated. Eventually, they bore no resemblance. The computer had not introduced random noise. The equations were deterministic. The divergence came from sensitivity to initial conditions. Lorenz developed an even simpler set of 3 equations and published the result in 1963. The solutions did not repeat periodically. They remained bounded and structured while never settling into a simple cycle. When plotted in phase space, they formed the shape later called the Lorenz attractor with 2 looping wings. The picture became an icon of chaos. Chaos in this mathematical sense is not mere disorder. It describes deterministic systems in which nearby states can separate rapidly. The atmosphere contains both predictable structures and chaotic growth of uncertainty. A planetary wave may be anticipated while the exact storms embedded within it remain uncertain. A blocking regime can provide extended skill. Convection can amplify small errors quickly. Lorenz did not derive one precise universal 2-week forecast limit from his 3-equation model. The familiar horizon near 2 weeks comes from broader studies of error growth in realistic atmospheric systems and remains a scale rather than a wall. Beyond that range, detailed initial condition forecasts lose much of their value. Statistical, subseasonal, and climate predictions can still have skill because they ask different questions. A forecast of the exact temperature in one town 30 days from now is unlikely to be meaningful. A forecast that a large ocean pattern increases the chance of a warmer month can be. Weather and climate prediction differ in what is being predicted. Lorenz later used a butterfly metaphor in the title of a 1972 talk. Could the flap of a butterfly's wings in Brazil set off a tornado in Texas? The question was not that one butterfly literally chooses one storm. Tiny perturbations can grow, but they can also cancel, remain small, or be overwhelmed by other differences. The metaphor describes sensitivity, not simple causation. A tornado does not exist because one wing moved. The atmosphere's future depends on details too numerous to measure exactly. Ensembles are the practical response. They do not defeat chaos. They estimate how uncertainty grows. Artificial intelligence has added a new family of models. Traditional numerical weather prediction integrates physical equations explicitly. Machine learning systems learn patterns of atmospheric evolution from large archives of analyses and observations. Several AI models can produce global forecasts quickly and achieve skill comparable to leading physical systems for many large-scale measures. By 2025 and 2026, national forecasting centers were actively testing and integrating machine learning with data assimilation, ensemble prediction, nowcasting, and physical models. The Met Office and Alan Turing Institute reported in July 2026 that their FastNet model produced physically realistic forecasts with accuracy comparable to the Met Office global model on several metrics. AI forecasting is no longer hypothetical. It also does not make physical understanding obsolete. A learned model depends on the historical data and analyses used for training. Rare extremes may be underrepresented. Climate change can move the atmosphere beyond some training relationships. Conservation laws, uncertainty calibration, interpretability, and local hazards remain important. A fast model can make enormous ensembles possible and reduce energy use. A hybrid system can combine learned efficiency with physical constraints. The future may not be a contest between equations and AI. It may be a forecasting system in which each corrects the limitations of the other. Nowcasting focuses on the shortest range. Radar, satellite, lightning networks, surface stations, and machine learning tracks storms over minutes to hours. A thunderstorm's current motion can be extrapolated. Growth and decay remain harder. Warnings are updated as rotation intensifies, hail develops, or rainfall repeats. At this scale, a forecast becomes a decision tool. Should a school move people indoors? Should an aircraft divert? Should a river gate be adjusted? Should a phone alert wake someone at night? Forecast quality includes more than physical accuracy. The message must arrive. The recipient must understand it. A warning must describe the hazard, location, timing, and action. Too many false alarms reduce trust. Too little warning costs lives. Uncertainty cannot be eliminated, only communicated. Robert Fitzroy's cone and drum faced the same problem in another form. A forecast exists to change what happens next for people, even though it cannot change the weather itself. The success of forecasting repeatedly created another temptation. If weather can be understood, perhaps it can be controlled. Modern weather modification begins with cloud microphysics. Some cold clouds contain supercooled liquid water, droplets that remain liquid below freezing. Introducing ice-forming material can change how crystals grow and how precipitation develops. Silver iodide has a crystal structure similar to ice. Dry ice cools local cloud air strongly. Hygroscopic particles can encourage droplet growth in selected warm clouds. Aircraft, rockets, or ground generators release these materials into clouds. This is cloud seeding. The important limitation is present before the first particle is released. Seeding cannot create a cloud in clear dry air. It cannot supply missing moisture, remove a strong inversion, or manufacture the lifting motion needed to sustain precipitation. It can only attempt to alter a cloud that already has suitable temperature, liquid water, airflow, and lifetime. Experiments show that seeding can modify cloud particles under some conditions. Demonstrating how much additional rain or snow reaches the ground is harder. A cloud cannot be repeated twice, once seeded and once untouched. Natural precipitation varies across short distances. Wind carries material away from the intended region. A microscopic change may disappear as the cloud evolves. Randomized experiments, chemical tracers, radar, aircraft measurements, gauges, and models help separate effect from natural variability. Some carefully studied winter mountain cloud programs support modest precipitation increases under suitable conditions. The estimated benefit is uncertain and cannot be transferred automatically to another cloud or climate. There is no demonstrated cloud seeding method for stopping tornadoes, preventing lightning, eliminating floods, or steering severe storms. Hurricanes once became targets. From the 1960s into the early 1980s, Project Stormfree attempted to weaken tropical cyclones by seeding outside the eye wall. Researchers hoped a new, wider eye wall would form and reduce peak wind. Some storms appeared to weaken after seeding. Later observations showed that hurricanes naturally undergo eye wall replacement cycles that can produce the same change. Researchers also found less supercooled water in the relevant parts of hurricanes than the original theory required. The experiment could not separate intervention from normal storm evolution. Project Stormfree ended, but the failure improved hurricane science. The difficulty is scale. A seeding plume may influence microscopic crystal growth in part of one cloud. A tropical cyclone processes heat and moisture across hundreds of kilometers while continually reorganizing itself. Explosives, ocean cooling, surface films, and nuclear weapons cannot remove that energy supply without creating larger problems. Human beings modify weather more effectively without intending to. Cities alter heat and roughness. Pollution changes aerosols and droplets. Irrigation changes humidity. Deforestation changes evapotranspiration. Aircraft create contrails. Greenhouse gases change the planetary energy balance. The most reliable form of weather control is therefore control of exposure. Drainage can carry intense rain. Building codes can reduce wind damage. Shade and ventilation can reduce heat risk. Warnings can move people away from surge, lightning, floodwater, and tornadoes. Forecasting respects the atmosphere's scale. It does not need to overpower a storm to reduce what the storm does to people. Weather describes the changing state of the atmosphere. Climate describes patterns, distributions, and ranges across longer periods. The distinction is often summarized as weather is what happens and climate is what is expected. The phrase is useful if expectation includes variability and extremes. Climate is not a 30-year average floating separately from storms. It includes the probability of heat waves, heavy rain, drought, frost, wind, and seasonal transitions. A changing climate changes the background in which weather develops. The laws of motion do not change. The amount of energy and water available to the system does. Carbon dioxide, methane, nitrous oxide, water vapor, clouds, and other atmospheric components interact with radiation. Earth receives mainly shortwave energy from the sun and emits infrared radiation according to its temperature. Greenhouse gases absorb and emit infrared radiation at particular wavelengths, reducing the rate at which energy escapes directly to space from the lower atmosphere and surface. The natural greenhouse effect keeps Earth's surface far warmer than it would be in a comparable atmosphere without infrared absorbing gases. Human activity has increased concentrations of several long-lived greenhouse gases, producing an additional energy imbalance. The ocean stores most of the accumulating heat. Land and atmosphere warm. Ice melts. Sea level rises through thermal expansion and loss of land ice. Weather then develops on a warmer planet. A basic thermodynamic relationship explains part of the change in rainfall. Near ordinary atmospheric temperatures, saturation vapor pressure increases by roughly 7% per degree Celsius of warming. This Clausius-Clapeyron relationship does not mean every place becomes 7% wetter or every storm produces exactly 7% more rain. Moisture supply, circulation, stability, storm motion, aerosols, and terrain also matter. It means a warmer atmosphere can contain more water vapor. When a storm successfully lifts and condenses that moisture, heavier precipitation becomes possible. Observations and attribution studies show that human-caused warming has increased the intensity and frequency of heavy precipitation over many land regions. The signal varies geographically and remains harder to detect where records are sparse. Flooding does not depend on rain alone. Soil moisture, snowmelt, river management, drainage, pavement, deforestation, tides, and construction in floodplains determine impact. Climate influence and local vulnerability meet in the same event. Heat extremes provide one of the clearest connections. Raising the average temperature shifts the distribution, making high-temperature thresholds more frequent and allowing more intense events. Changes in soil moisture and atmospheric circulation can amplify individual heat waves. A blocking high can persist as it always could, while the air beneath it begins from a warmer baseline. Event attribution uses observations and climate models to estimate how human influence changed the likelihood or magnitude of a particular event. The result may say that an event became several times more likely or a certain amount hotter. It does not say climate change was the only cause. Weather still requires the immediate circulation pattern. Attribution compares worlds. One includes observed greenhouse gases and other human influences. The other approximates a climate without them. The difference measures how the odds were loaded. Drought is more complex because several definitions exist. Meteorological drought concerns lack of precipitation. Agricultural drought concerns soil moisture and crop stress. Hydrological drought concerns rivers, reservoirs, and groundwater. Ecological drought concerns ecosystems. Warming increases evaporation demand and can intensify drying where moisture is limited. Changes in precipitation, snowpack, vegetation, and water use can reinforce or oppose it. A region can receive near normal annual rain and still experience drought because the timing changes or heat removes water faster. Fire weather combines dry vegetation, heat, low humidity, and wind. Climate influences fuel dryness and season length. Ignition may come from lightning, power lines, machinery, or people. Land management changes fuel structure. A fire is not weather alone, and its behavior is inseparable from weather once it begins. Wind carries embers. Dry air increases evaporation. Unstable conditions build plumes. A large fire can generate pyrocumulonimbus clouds that produce lightning and inject smoke high into the atmosphere. Fire creates its own local weather while remaining inside regional climate. Snow and cold do not disappear from a warming world. Winter storms continue because temperatures can remain below freezing and atmospheric dynamics still transport cold air. A warmer atmosphere can sometimes increase snowfall where conditions remain cold enough because more water vapor is available. Over longer warming, more precipitation shifts from snow toward rain. Snow seasons shorten in many regions, and melt begins earlier. One cold event does not disprove global warming. It describes one place and time inside a global trend. The same reasoning prevents every unusual event from being blamed automatically on climate change. Science asks which mechanisms are affected and how confidence differs. Tornado trends remain uncertain. Tropical cyclone rainfall and the proportion reaching high intensity have stronger physical and observational support than a simple rise in total cyclone count. Heavy rainfall has stronger global evidence than changes in every local wind extreme. Heat is clearer than hail. The responsible answer varies by hazard. Weather science also observes feedbacks. Loss of snow reduces reflection and exposes darker land that absorbs more sunlight. Drought reduces evaporative cooling and allows more energy to heat the air. Wildfire changes vegetation and surface properties. Urban expansion adds heat and runoff. Irrigation cools some regions through evaporation and adds moisture. A city, forest, farm, and ocean do not merely receive weather. They help shape the lower atmosphere. Climate services translate these changing probabilities into building standards, reservoir rules, agriculture, health planning, and emergency systems. A storm sewer designed from an old rainfall record may fail if extreme rainfall changes. A coastal defense designed around an old sea level loses protection even if the meteorological surge is identical. A crop planted according to a past frost date may encounter a shifted season and a late cold outbreak. Adaptation uses climate to prepare for future weather. Forecasts use the current atmosphere to prepare for the next hours and days. The two timescales meet. Seasonal outlooks use slowly varying conditions such as ocean temperature, soil moisture, snow cover, and stratospheric winds. Subseasonal forecasts attempt the difficult range from about 2 weeks to 2 months. They cannot specify the exact rain in one town far ahead. They can sometimes identify increased probability of regimes, warmer conditions, a wet period, tropical cyclone activity, or displacement of the jet stream. Sudden stratospheric warming illustrates the connection. During some northern winters, temperatures rise rapidly high in the stratosphere and the polar vortex weakens or splits. The disturbance can influence tropospheric circulation weeks later, increasing the probability of cold air outbreaks in some regions. The effect is not automatic and not identical each time. Information from far above ordinary weather can extend useful guidance below. The Madden-Julian oscillation is another source of subseasonal skill. It is a large eastward moving pattern of enhanced and suppressed tropical rainfall that circles through the tropics over weeks. Its convection can influence monsoons, tropical cyclones, and jet stream waves. When models capture its phase and propagation, they gain information beyond ordinary day-to-day predictability. The atmosphere is chaotic without being memoryless. Oceans, soil, snow, ice, and slowly evolving circulation patterns retain information. Forecast skill depends on asking a question matched to the timescale. Tomorrow's rain can be forecast in detail. Next month's rain may be expressed as probability. The climate decades ahead can respond strongly to greenhouse gas scenarios even though no one can forecast the exact storm on a particular future date. This does not contradict chaos. Climate projections concern statistical behavior under changed energy balance, just as the seasonal warming from winter to summer can be predicted without knowing the weather of every summer day. Weather is the path. Climate is the terrain and distribution of possible paths. Both are moving now. The portion of air we have followed has traveled through both. Its immediate motion came from today's pressure pattern. Its water content depended on ocean temperature. Its storm formed within a season, a circulation regime, and a changing climate. The drop falling from it cannot reveal which level caused it. Science reconstructs the levels through observation and comparison. The first raindrop from our cloud begins falling through air that is not uniform. Near the cloud base, the air may be dry. Part of the drop evaporates. Evaporation cools the surrounding air, making it denser and strengthening the downdraft. If the entire drop disappears before reaching the surface, a streak called virga hangs below the cloud and fades into clear air. A person underneath may feel a cool gust and receive no rain. This drop survives. It accelerates until drag balances gravity and reaches a terminal speed determined largely by its size and shape. Wind moves it sideways. Turbulence gives it a path that no forecast model could follow molecule by molecule. It passes through the final meters and strikes soil. The impact can release a familiar smell. Dry ground contains plant oils and compounds produced by soil microorganisms. A falling drop traps tiny air bubbles against the surface. The bubbles rise and burst, launching microscopic aerosols into the air. Some of those molecules create petrichor. The scent is not rain itself. It is chemistry lifted from the ground by rain. the water begins another set of paths. Some infiltrates soil. The rate depends on pore space, roots, compaction, slope, previous moisture, and rainfall intensity. Dry ground is not always absorbent. Fire or drought can leave water-repellent surfaces. Saturated soil has little storage remaining. Pavement offers almost none. This is why flood forecasting requires more than forecasting precipitation. Meteorologists estimate how much water will fall, where it will fall, and how long the rain will remain. Hydrologists ask what the land and river will do with it. Soil moisture, snow, reservoirs, vegetation, terrain, and previous storms become part of the answer. Every impact forecast is a chain. An uncertainty at one link moves into the next. Other water remains near roots. Plants draw it upward and release part of it through stomata in their leaves. This transpiration returns vapor to the atmosphere. Some enters groundwater and moves slowly through rock. Some remains in a lake. Some freezes into snow or glacier ice. Some reaches the ocean within days. The water cycle is not a perfect circle completed on one schedule. It is a network of short and long storage. A molecule may pass through the atmosphere several times in a month and remain underground for centuries. Weather is the fast, visible part of that larger movement. The cloud that produced the drop is already changing. Precipitation removes water and drags air downward. Evaporation cools the outflow. The gust front travels ahead. New clouds may grow along it while the original updraft weakens. The weather system loses the clear identity it seemed to possess on a satellite image. Its air mixes with surrounding air. Its moisture enters soil, rivers, plants, and other clouds. Its energy spreads through wind, waves, phase changes, and heat. There is no precise instant when one weather system ends and another begins. Meteorologists draw fronts, centers, and boundaries because recognizable patterns are useful. The atmosphere itself contains gradients. A front weakens in one place and strengthens in another. A low fills. A new wave grows along the old temperature contrast. Yesterday's tropical moisture enters tomorrow's mid-latitude rain. Weather continues by losing its previous shape. Forecast verification must account for this. A model can predict a storm correctly and place it 50 kilometers from the basin that actually floods. It can predict a high temperature within 1 degree and still miss whether a road freezes. It can identify severe storm conditions across a region without knowing which town will receive hail. Accuracy depends on the decision being made. A farmer, pilot, emergency manager, river forecaster, and person planning a walk do not need the same forecast. Probability allows one atmosphere to serve several decisions. A 70% chance of rain is not a promise that rain will occupy 70% of the day. It describes confidence under a defined forecast method and area. An ensemble spreading tropical cyclone tracks does not mean the storm will fill every path. It shows how plausible futures diverge from uncertainty in the present. The atmosphere is chaotic, but it is not arbitrary. A small error can grow enough to change the later position of a storm. It cannot erase the mountain that forces air upward, stop Earth rotating, or make winter sunlight equal summer sunlight. Large structures constrain the smaller motion for a time. This is why forecasts can be imperfect and extraordinarily useful. A jet stream trough may be predicted days before the exact rain bands form. A tropical cyclone's broad steering can be known while its eye wall reorganizes unpredictably. A sea breeze can be expected while the location of its first thunderstorm remains uncertain. Different scales carry different amounts of predictability. The same is true beyond ordinary weather forecasts. Ocean temperatures can tilt seasonal probabilities. Snow, soil moisture, and stratospheric winds can provide memory over weeks. Greenhouse gases alter the statistical background over decades, even though the exact storm on a future date cannot be calculated. Tomorrow's weather, next month's outlook, and future climate are different prediction problems. Chaos does not make all of them equally unknowable. Tonight's atmosphere contains those timescales at once. Near the ground, friction slows the wind. A short distance higher, the boundary layer responds to heat stored during the day. Farther above, broad currents follow pressure patterns across countries. Near the tropopause, a jet stream curves across a continent. Over an ocean, water enters the air invisibly. Inside a cloud, droplets form on salt, dust, smoke, and other particles. Somewhere, lightning separates charge. Somewhere, a balloon is rising with a radio sonde. Somewhere, an ensemble is diverging. Somewhere, a forecast is being translated into a warning. The atmosphere has no walls matching the lines on a map. Smoke crosses oceans. Dust from the Sahara reaches distant ecosystems. Moisture evaporated from one country falls in another. Volcanic particles spread through the stratosphere. Air inhaled tonight may have crossed a sea, a forest, a desert, or a city before entering the room. The gases are shared even when the weather is local. The broad system can now become small again. If the sky outside is clear, weather has not stopped. Dry or sinking air may be suppressing cloud. The surface may be cooling beneath stars. A light wind may be balancing pressure and friction. If rain is falling, every drop has passed through evaporation, transport, cooling, condensation, growth, and descent. If fog covers the street, the surface and lowest air have approached saturation. If snow is falling, each crystal carries a record of changing temperature and humidity. If wind presses against a window, the pressure field extends beyond the horizon. There is no need to identify which pattern is present. The atmosphere continues without being interpreted. Pressure adjusts. Heat moves. Water changes phase. Forecast models update as new observations arrive. The portion of air followed through this story has already mixed into other air. It no longer has one border or one destination. That is not the end of its motion. It is how weather works. Patterns form because the atmosphere contains structure. They dissolve because the fluid never stops moving. Tomorrow will contain much of the same matter in another arrangement. A front will still lift warm air. A mountain will still force ascent. Earth will still turn broad winds. The ocean will still store and release heat. The principles remain while the details change. For now, the air near the room can remain only air. Breathing takes a small part of the moving atmosphere and returns it. A cloud can continue crossing the dark without being followed. A drop can reach the ground without being counted. A forecast can update while no one watches. The planet turns beneath its thin, restless atmosphere. The system never becomes completely still. It only becomes quiet at the scale of the room. Sleep well. Good night.